Okay, please proceed.
Yeah, hello, good morning, everybody. My name's Andy Götz. I'm a research scientist at SDSC, and it's a pleasure to have you all here for our Advanced HPC CI webinar series. And so today we have a great speaker, Fernando Garzon. He's a data scientist and software engineer at SDSC. Fernando has been with us since August 2022, and he has actually a background in physics and transitioned into scientific computing and software engineering, where he's focusing on building reproducible, scalable workflows for research and HPC environments. So he's working on many different things, from data engineering, backend development, distributed systems, and modern AI ML pipelines. He's also part of our Open Science Chain project, where he helps design and implement secure high-performance architectures using Python, TypeScript, and blockchain technologies. And he's really passionate about bridging the gap between exploratory research code and production-ready scientific software. And today he's going to talk about architecting reproducible science, a practical path beyond the notebook. So, Fernando, please take it away.
Thank you, Andy. Thank you very much. So I'm going to share my screen real quick, and I make sure I'll be able to share computer sound. Yeah, you should be hearing my computer. So first of all, thank you, Andy, for that great introduction. Thank you all for attending this talk. I am very happy, very grateful that you are all spending your time here. I hope it is worth it for you. So it is a great pleasure for me to be here to be your speaker this morning. My name is Fernando Garzón. The title of this talk is going to be Architecting Reproducible Science, a Practical Path Beyond the Notebook, namely the Jupyter Notebooks. So this is going to be a talk about applying software engineering principles to improve your HPC, and I hope you enjoy it. So Andy already made a quite good introduction about myself, but if you want to know a little bit about me, a little more, so I work as a software engineer at SDSC, have been here for about 3 years now. I also work on software development projects. I have a great experience there, so I want to share all that with you today to some degree, hopefully, and I consider myself to be an automation enthusiast, passionate also about software development, DevOps, all this really cool stuff. The outline is going to be very simple. So first, I'm going to make a little intro to one problem that you all encounter on your daily basis, which is the unreproducibility horror or unreproducibility problem. Then we're going to talk about notebooks. Notebooks, for the most part, they don't scale well, but packages do. Then we're going to take a look at how you can take your code into production. Then, of course, if we're going to talk about production, we need to talk about GitHub Actions, something I guess most of you have experience with. And finally, we're going to talk a little bit about MLOps, how you can become more attractive to potential employers. And finally, some final remarks. So let's dive into it. So first of all, I would like to share a quick video. I think this is
Meet
it.
Milena, a brilliant.
Sorry about that. Can you guys hear the
Yes.
video? All right, great. So I'm gonna restart the video.
Meet Milena, a brilliant computer science grad student at UC San Diego. While most of her classmates chase deadlines, Milena chases decades, 15 to 30 years into the future, predicting San Diego's housing prices. For months, she devours every paper from 1920s econometrics to last week's preprints, fine-tuning models in her trusty Jupyter Notebook. After countless experiments and spotless backtests, she lands the model shockingly accurate, lightning fast, a future forecasting marvel running on her laptop. A top data science journal publishes her findings. Word spreads. A major real estate firm calls, "Show us the magic." They set up a meeting. Milena arrives, she feels confident. Stakeholders lean forward, coffee untouched. She opens the notebook. Cell 1, data ingest, runs perfectly. Cell 2, feature engineering, green check. Cell 3, baseline metrics, impressive nods. She suddenly remembers cell 7 holds key helper functions. She jumps, executes, then returns to cells 4 and 5 for advanced transforms and cross-validation. Time for the crescendo. Cell 11, the training loop. She hits enter. Laptop fans roar. The screen stalls. Her pulse spikes. She skips cell 6, the optimization routine that prevents memory overload. The notebook locks. Her model collapses. And so does the room's enthusiasm. Stakeholders exchange puzzled glances and thank her for her time. Opportunity evaporates like coastal fog. Milena stares at the frozen screen. Lesson crystal clear. Even genius models need production-ready workflows. Because in data science, especially when billions are on the line, order of execution can make or break the dream. Will you be the one who can help Milena land her next business opportunity?
All right. I hope that helps a little bit with my introduction. Okay. So let me start by pointing out the following. So I'm gonna start talking about the unreproducibility problem. So there are at least two meanings for the word reproducibility, at least two that I can find. The first one is, for example, if you have your Jupyter notebook, thinking about Jupyter notebooks, you can think of them as a very reproducible artifact in the sense that it is very easy for you to copy paste it from your laptop to your friend's laptop, let's say, and have it run it there and reproduce virtually the same results that you had in your laptop in the first place. You can also copy paste the same notebook into an HPC system, for example, TSC or Expanse or whatever really cool cluster that we have at SDSC, and you can also have it run there. I mean, obviously copying the right requirements, setting up the right environment. You can always copy paste it and have it reproduce the same results that you had initially in your laptop. You can also even go into the cloud, AWS or GPC, wherever, Google Colabs, and you can also have it there running and reproduce the exact same results. And that's fairly simple. That's something that I guess most of you know how to do very well because it's not a complicated topic. However, this isn't going to be a talk about copy pasting Jupyter Notebooks. That would be very, very boring. Plus, there is no real use in that. So there is a second meaning in which the word reproducibility actually has a really deep impact and a really deep. There's a really deep content to it that I would like to discuss today with you. So let's recap a little bit on what happened on the video. So what do you think was Milena's error on the video? So if you recall, the silly mistake that she made was that she forgot to run one or two sets. She skipped a couple sets. That was basically it. Wasn't a terrible mistake, but bad enough, I guess. And that mistake could have caused the loss of, in this case, billions of dollars in this hypothetical case. So what if you could deploy your code into a system and have it run there and making sure that your code won't skip any cells, so to speak? What if you can deploy your code, which is beyond copy pasting, but what if you could deploy your code in any system and make sure you will have always predictable runs, almost 100% deterministic, very controllable, all that. And not only that, but what if you could deploy your code so that it can serve, for example, thousands of clients at the same time and it still be predictable? It won't skip any cells, keep it controllable, and almost 100% predictable. Well, what if you could do that? So if you think about that, and that is actually possible, if you think about that and you think about a way to do that, then the word reproducibility acquires another meaning or another sense. And in software development, in software engineering, that the word reproducibility can be switched to the word scalability. So how can you make your code in your Jupyter Notebook more scalable? That is the real challenge here. What if you could make your code scalable to hundreds or thousands of concurrent clients at the same time and reproduce really good results, being controllable and almost deterministic and all that. So this is what this talk is going to be about. So one way you can achieve that is by migrating your Jupyter Notebooks into Python packages. And there are techniques to achieve just that. So I'm going to show you that a little later during this talk. So this talk is not to denigrate Jupyter Notebooks. I mean, not even close. After all, and I'm sure you have experience with Jupyter Notebooks. You know that these notebooks are great for exploration, visualization, changing stuff on the fly or editing stuff on the fly, like a variable value, and see in real time its impact on the code or in the run. It is useful for plotting, seeing graphically what's going on in your code. It is a really good tool after all. But Jupyter Notebooks are usually used to scale. They are not the main artifacts that developers or engineering teams use to scale. Now, to be 100% accurate, some teams do actually use Jupyter Notebooks to scale their code. So it is known to happen from time to time, but more often than not, what they usually do is they take their code into Jupyter Notebook and they migrate that code into a Python package. And why do they spend so much time and resources doing that? Well, because Python packages are basically ready to go. If they're built right, and if they're built right, they're ready to go. They're small for the most cases. They're lightweight. They are very easily deployable in any system. Doesn't matter the OS. Essentially, you can deploy them on every system. They are a lot easier to test than a Jupyter Notebook, and they're very, very easy to scale. So that's why they spend so much time doing that. That is a standard practice in the industry and has been for quite some time. So I'm gonna teach you today, hopefully, I'm gonna show you how you can do that. So I'm gonna show you a little process where we will grab a notebook and we will migrate that code into a Python package. I have it run locally. I'm gonna upload this code or this package into a repository. You will see that, and you will then see it running in another system, namely TSCC. So let's do that. So that's how you do productionation of code. So let's start here. So I have this repository, this GitHub repository that I will share hopefully after this talk, but you will have access to it later. And in this GitHub repository, you have one Jupyter Notebook, which is this one over here. So what you need to do first, there is a little tutorial here, but what you want to do first is just download the repo and execute this Jupyter Notebook. It's fairly simple to do. I have provided all the tools to do that through the command line. So if you do that, hopefully I can show you what is it that I did. I created an environment. Take a look at this. I'm using actually Windows because you can use anything to run this stuff. So that's why I mentioned they are very reproducible. You create an environment and you simply run Jupyter Notebook and you can have your notebook run. So that's very simple. Everyone knows how to do that. And if you do that, you will see this notebook over here. So what is this notebook about? So let me just move this over here. Okay. So this is a very simple notebook. We built it to explore a small convolutional neural network for MNIST digit recognition. So we import Python, so you can see all the import statements over here. We import PyTorch, sorry. And we define training settings like batch settings. You can see all the variables over here. Batch size, learning rate, number of filters, all that fun stuff. Then, very simple, we define a simple CNN called myNet. one computational layer, two fully connected layers, a log softmax output for 10 digits classes. And then we define a training loop. You can take a look at this in your own time. It's not really complicated. It's really, really simple stuff. We define the train and test functions over here. You can see that the code is capable of recognizing if it's running on CPU or GPU automatically, and then it loads the MNS with normalization using PyTorch data loaders. The notebook intentionally limits the batch size so that it doesn't take forever to run. But if you have it get it running, so for example, you see here that it is using CPU because it's running in my laptop. And if you have it run, you will see here the epochs that it uses to train the model. And you can see some time over here. So it is capped to a maximum amount of batch size, so it doesn't take forever. But you can do it on your own. So this is basically it. Then you can see some plots over here, see how the accuracy and the epoch, how the accuracy grows as epochs also, passes. And you can see some predictions here, some numbers, some nice cool stuff. So all this you can do on a Jupyter Notebook. So that's pretty. That's what a Jupyter Notebook is for. So what we are going to do is, okay, we have this. Let's see how we migrate that code into a nice little Python package. So we're gonna go into the steps here real quick. It's not gonna take that much, but essentially, what you will do is to create an environment. I have added instructions for either Windows or Mac OS. So you create an environment, you activate it, you install a few dependencies. You install even more dependencies over here. You install Torch and Torch Vision. And then once you have done all that, we're going to use a tool called NVS. So NVS is the tool that is going to help you migrate your code from this Jupyter Notebook into a Python package. First of all, you need to move or copy paste your notebook into this folder. And then we're going to take a look at this notebook over here. So this notebook over here, which is this one. And if you want to go into the repo, you can check the NVS folder. It has this repo. It's the same repo. It's the same notebook, I'm sorry. But here, this notebook has some important labels that you need to take into account before you migrate into a Python package. So first of all, this first cell, this default line over here, you need to always put that in the first cell, or at least where you want to start the migration process. And then there are two important parts. So first of all, you will add an export statement on each cell that you want to migrate into your Python package. There are a few cells that you want to migrate. There are a few cells that you do not want to migrate. The cells that you do not want to migrate are a couple of them. First of all, the training loops. So if you take a look at the training loop, this one, I do not migrate that. What is the reason for that? The reason for that is that if you migrate this into a Python package and you install it into any service, any VM, for example, or any other system, every time you download this package, it will run a training loop. And that is a waste of resources and time because you don't want that to happen right there. You want to download your package and you want to run your heavy workflows, namely the training loop, at your own pace, controllable. You don't want that to happen once you download the package. The other cells or other type of cells that you don't want to migrate are the plotting cells. So for example, let me go back to the previous one. These plotting cells, you don't want to migrate those. You want to keep them out of your Python package. You don't want that. Consumes resources, consumes time, so you don't want that in your Python package, at least not at the installation time. What do you want to migrate? So you want to migrate the imports, of course, important variables. Maybe you want to migrate this, maybe not, because maybe you are able or capable to modify your Python package. So these are either pass has parameters or are hard-coded, whatever you want. You can do whatever you want with your Python package. You can decide. You want to migrate classes. You want to migrate important functions. This one is also an important function. And that's pretty much what you want to import, right? Okay. So let's say you have done all of this, right? You edit this Jupyter Notebook. You add these labels over here, the export labels. And then what you want to do, so here is it is all explained over here. What you want to do is run this little command over here. So one thing that I may have missed is that, let's say that you don't have one notebook, but you have several notebooks, or maybe you have a very big notebook and you want to split it into different smaller notebooks. So if you want to copy paste all of that, you need to keep in mind this lexicographic order here. That is very, very important for the tool to work correct. So that is actually another reason why you want to migrate to a Python package, because Jupyter Notebooks have the tendency to grow out of control. And I know that because I've been there, been an academic for most of my professional time, my professional life, and I've seen very big, horrible Jupyter Notebooks grow and grow and grow. So you wanna keep them as clean as possible. And once you have your Jupyter Notebooks there, you will run this little command over here. So I'm gonna warn you, because I'm sure at this point that if you do everything right and you run this on your own personal notebooks, you'll probably see that it won't produce a beautiful set of files for your Python package. More often than not, it's going to be a little ugly. The reasons for that: first, as I mentioned, Jupyter Notebooks have the tendency to grow out of control sometimes, especially if you probably don't have much experience in the best coding practices. And second, well, they are also very large. They're also very large. So what you want to do before running this is have your Jupyter Notebook code organized. And you can do it yourself by hand, or you can use an AI tool. For example, I often use Cursor because it's very, very cool. If you don't have much experience creating this type of packages, you can ask Cursor to help you, or any AI language, LLM model, to help you organize your code in a way that is in your Jupyter Notebook, so that it is organized, that it has some consistency, that it is well modularized, all that, so that when you run this little command over here, it creates somewhat beautiful on your Python package. This is this is very important. When you run this command, you will generate this file. This file have important information about your new package. A version, for example, is very important. You want to keep versions, or you want to keep your code version requirements. All that is in this file over here. Then you will run this command over here, and it will produce even more files. It will create a tag version. It will install Git hooks, all that, because you really need all that. And then once you do all that, you will be generating, or the tool will generate somewhat similar to a Python package, somewhat that's is close to what you want to deploy in your systems. So as I mentioned, it is highly probable that this Python package doesn't look beautiful, maybe look a little messy, a little too big. Maybe you don't understand what you just produced. But thankfully, nowadays, we have really cool tools to fix all that. So even if you fixed your Jupyter Notebook previously, you still want to do some linting on your newly produced Python code. So I have added a little prompt over here that you can use on any LLM. Now this talk was prepared 1 year ago, so we had different LLM models back then, but nowadays I would suggest using, for example, ChatGPT 5.3 codex is really good for this. Sonnet latest version is very good for it. Opus is the one that they say is the very best at this time for coding. So you can just have this prompt, feed that into your model, feed the code there, and hopefully it will help you organize your code in following this solid paradigm for building applications. So here you can read about what Solid is. It's a standard in the industry. It's very used, especially for Python packages, so that you can create something that is small, testable, easily deployed, easily fixable if anything breaks. And hopefully, if you do all of this, finally, what you need to do at the end is just build your package. So if you run this, you will build your package, your wheel, essentially, in the dist folder. That's how you migrate. Now, once you have that, you can install your package in your local environment and have it run there. And I'm going to show you what it looks like. So I have previously done all that, of course, because it takes quite some time to do all that. So I have up to this point, I have done all those steps. I want to show you the code a little bit. So this is how the code will end up looking. So on any NBS, you will see the initial Jupyter notebook that I have created. I'm going to close this, probably have one now. Show this. Here you can see the Jupyter notebook that I copy pasted first. And in here, in this folder, you will see the created code for the Python package. So you can see here the code for the training loop for everything. I'm sorry, yeah, for the training loop, because not for the training loop, but the important functions that define the core of your package. And you can see here some other fun files that you need to have if you want to have Python packages. Init file is very important. You always want to keep that and all that. If you run this, so now if you have created this and if you have a command line function over here, namely the main function, you can use that to run your code into your local deployment. And if you do that, you will see something like this. So hopefully this will work. I want to do probably this. So I'm gonna just run it in my command line. But if it fails, I hope you see how it ran in the past. So it takes about this much time in my CPU to run all this, right? 50 seconds per epoch, but you can see it is currently running. It is producing almost the same results as the Jupyter notebook over here. So if you take a look at these results, probably they are almost the same. One little thing that you may be seeing is that the training time here takes little time, 5 seconds. The reason for that is because this Jupyter notebook has been capped to a certain amount of batch size. So it doesn't take all the samples. It takes just a few of them. Okay, so that's pretty good. But it may happen that sometimes these run-ins may take a seriously long time. It's taking 20 seconds at this time. Probably you don't have that much time. So you want to test it faster. You want to have some way to test it a little faster than that. So here's another software engineering principle, which is the unit test. So unit tests are a small test, very modular test that you use in order to test your code without committing too much resources. So what do I mean by that? So you see here, when you run a training loop, it will take an awful lot of resources and an awful lot of time. But if you use unit test, and I advise you to always do that, and create this little file over here, these unit tests are very simple. They are just simple assertions that they assert the size of the tensor, the size of the samples, all that. They are very easy to build. And if you do that, and if you run them, you will see here, it doesn't take that much time to run. So you will run this here. I have run that previously so that it doesn't take that much time, but you can see here, it is quite fast. And what it does is just simply take your code, and it doesn't commit too many resources. It's only a very, very small amount of resources. And it runs basically some self-consistency checks of the main code over here. So you don't need to run the whole thing. You only need to run unit tests. Unit tests are highly encouraged to run and to create and to keep, and also keep a basic amount of coverage. I have it at 65%, but you can have it higher than that. So unit tests are really, really important to do, to create. And then it comes the fun part. The fun part is this. So now that you have your package created, your package is in this dist folder, is one of these last 3 or 4. It's one of them. I don't remember. It's the last one I created. Once you have it, I think it's 0.9. Once you have it, you can upload your package into a remote repo, not GitHub repo, but a remote repo called PyPy. So PyPy is a repository for Python packages, and if it is open source, so you can upload your code over there. And if you want to do that, what you need to do is you need to create an account for yourself, create an authentication token, such as this one over here. Of course, I'm not going to share my token. But if you do that, you are able to upload your wheel over there or your package over there. So this is what it does. So I have run that previously because I don't want to do that right now because it might take some time. But once you run this and you upload your package into this repository, you will be able to see it somewhere over here. So I have done that in the past. I've done it several times. But if you do it, you will be able to see it right here. What happens when it's there? When it's there, what will happen is that you will have it available at any time and for you to run whenever you want, whatever you need it to run. So I'm going to demonstrate just that. So you have seen I've been running this on my local laptop, my local repository, but previously, before this talk, I did run this on TSC. So for the ones who don't know, TSC is one of the clusters at SDSC. And it was a very, very simple run. So I'm going to show you that because if I do it live, it might take some time. But essentially what I do is create a job, load Python 3, module load Python 3, and create an environment. So it's basically the same steps that I did on my local laptop. I upgrade pip because it's the thing to do. And then somewhere over here, I install the version that I need to use of this package. I install it. There is a lot of caching going on, so almost all requirements are already satisfied, so it doesn't take that much time. But the line that I want you to take a look at is here. So in here, you can see the environment is activated. You can see that I run basically the same line that I run in my laptop, but this is the SEC. And you can see here the run, essentially. You can see here the training loops. I'm sorry, the epochs is 5. So you have all the training loop over here, 5 epochs. You can see here a very big time for the first epoch and then very small times for the subsequent epochs. So if you recall correctly, well, first of all, first epoch takes this time because there is a lot of warming up and starting time that takes place on this first epoch, but there is a lot of caching afterwards. Then you don't need that much time to run the loop. Then every subsequent epoch will take no more than 3.3 seconds apparently. If you recall correctly, in my laptop, it was taking 14 seconds for every epoch. So it is certainly an improvement. Take into account that here I'm using GPU, namely it is using CUDA to run all of this. So you can see here that it is actually using the resources of the service or of the system that I am requesting. Okay, so enough of the manual part. That is pretty much the manual part. Then we are going to go into a more fun part, hopefully. And then now I'm going to talk about GitHub Actions real quick. Hopefully I have some time yet. So, okay. Okay, so what have we done so far? So we have our little Jupyter Notebook. We implemented a technique to migrate that code into a Python package. And this Python package, as you can see, it can be run in my laptop, it can be run in TSC, it can be run virtually anywhere. And you might be saying, well, isn't that the same that we were doing with the Jupyter Notebook, copy pasting in and doing the same? Well, this is a little beyond that copy pasting. First of all, we have a repo, a remote repo, PyPy, where we host the code and you can download it on any system you want. So there is no actual copy pasting happening. But also, with the Python package, we have the advantage or the capacity to implement some automations that are easier to do on the Python package than are easy to do on the Jupyter Notebook. And GitHub Actions are the first step on the automation process. So what are they? They are pipelines. They're automated pipelines that help you deploy your code easier, faster, reliable, or in a reliable way at least. And it's actually reproducible, at least scalable in the second sense of the word that I mentioned earlier. So I'm going to show you the code real quick. So I have two pipelines, publish pipeline and release pipeline. The release pipeline is this. So first of all, I have two branches. I have develop and master branch, and the release branch is used when I do a push on develop. This will happen. If the commit of said push has the word release, this will activate or trigger the execution of this pipeline. And what that means is that this pipeline will essentially do the same as I did in my laptop, which is it will create a Python environment. This is Linux. So the VM where GitHub runs this is Linux. So I have to be careful here, but it does essentially the same. Install the requirements. I take all the Windows friendly requirements out of the way because I don't want that. But I install the ones that are useful for Linux. So I do that. Essentially the same stuff. And once it is running, and once I install the package, of course, and once the package is there installed, I run some tests. So this essentially is the same unit test that I run in my local laptop. And I set a condition here that it should fail if the coverage is under 75%. That coverage means the lines of code that are actually covered by the unit test. If it all succeeds, it will create another branch with the name commit message name. And there you go. So I'm going to just do that real quick. So I'm going to do that real quick because we're running out of time. So I'm in branch develop, as you can see here, and I have added a few, if you take a look at here, I have added a few changes. Namely, I have added a change that I will cap the training loop so that it doesn't take forever to run. I have added some tests for that, and I have changed the version over here. I have bumped up the version to 0.9. So I'm going to do that. I'm going to use the git command line. I'm going to use release 0.9. Hopefully it will all work live. Sometimes it doesn't, but hopefully it will. So you do your little push, it all works out, and you go here into the actions, and you will see here the action actually taking place. So it takes a while to run. So I'm gonna take a look. I want you to see a previous run that I did before this talk. So essentially that's what happens here. So, well, first of all, set up a job and it sets up the Python version. Install full requirements. You can see here one thing that you may want to do, since this is, well, this job over here, this pipeline is running on Linux and it's running also, I believe, on CPU for sure. So for these pipelines, you can remove all the GPU related stuff so that it can be done a little faster if you want, because it takes some time to install all this GPU related stuff. So you want to make it faster, you can remove that just for this pipeline. You run the test, tests are above 75%. Then if you do it all right, you create a new branch called release 0.0.8, and that release has been created. I deleted it because I didn't want to keep all of them running, but that release branch was created previously. If all is working fine. I should be seeing, okay, it's gonna take a while to do this. It's gonna take a little while, but while that happens, I can show you the other pipeline. So once this release pipeline runs and is working, you can also use this another pipeline, which is the publish pipeline. The publish pipeline is used to publish a new version of your Python package into your repo, into PyPy, namely. So if we take a look at that, at the publish pipeline, it is a push on master branch. In this case, it isn't on develop branch. It is on master branch. It does essentially the same. I think in this one, I didn't run the unit test. I only built because the unit tests were run on release. I don't run them in here, but I build the wheel over here, and I just publish that on pipe. Take into account that if you want to do that, you need to create a secret with the authentication token or the API token for PyPy that you had created when you created your user for PyPy. So if that all works, you should see maybe this already finished running. But what I want you to show, hopefully if time permits, is that, okay, this ran perfectly. Since this ran perfectly, we should be seeing here a new branch, which is release 0.9 over here. Great, we have this release branch, and I'm going to create a pull request. Hopefully this will work really easily. I create a pull request, I check my code, I review it, I say, great, it's perfect, and I merge it into master. So that merging into master should trigger the second workflow, and you can see that over here. The second workflow is here, and it's been triggered over here. It shouldn't take that long. This one is usually a little faster, but if it does succeed, we should be seeing something here, which is the latest version is 0.8, and if this succeeds, we should be seeing an upgrade over here for version 0.9. Yep, it seems that it's happening. Yep, it's gonna happen. Yay. Great. So if I do this over here, great. So I have uploaded or have created a new version for this package over here, and it's ready to go, ready to install, ready to be used anywhere. What's next? You might ask, what's next? So yeah, that's pretty cool. I can automate the new version, the uploading of the new version. So what can I do later? What you can do later is, if you're using a system, the SC or the cloud, wherever, you can create script, a code, a package that calls this package, that does some pip install in the background and installs this package, and then you can run it wherever you want. Essentially, that's what you can do. And this is what I do over here. Actually, I think I have some time. I'm gonna download the latest version of this. Probably not, because I need to get this running. Probably yes, I was able to do it. But if I do this, I should get the new version of the package. There is a lot of caching going on, some warnings that's been known to happen. And one thing you can do is run the new code. So the new code will have, if you remember correctly, it has some capping on the train batches and on the test batches, so it doesn't take forever. And if you do this, you will be running this package over here. It will take a little while. First epoch always takes some time. But essentially, that's what happens. You can automate all that really, really, really easily. So I think I have some time. Maybe it will take some more seconds to finish the run until it's saved. Anyway, maybe in 1 minute I will show you that. I think that covers pretty much it for the time we have. Finally, what I would like to talk about, let me just check this. Okay, it's gonna take forever to run, so I'm just gonna continue with this one. So the final part that I would like to talk about is, what is this used for in a real world? So what I have done or work we have been discussing up to this point is an intro to something called MLOps. MLOps stands for machine learning operations, but it can easily be translated to AIOps. So, for example, if you are developing large language models, you can also use all these techniques to automate the deployment of such models, and you can use them in any system. Now, if you become the kind of developer who can actually deploy this kind of stuff in this manner, at least, and you can show in your portfolio that you're capable of managing this type of workflows and pipelines, and you can, for example, grab this code and deploy it into an AWS GPU or AWS instance and having trained it there and show the results, it is actually a very good sign up for employers. It's a very good marketing strategy of your skills. It is something that is currently paying off. The market is actually a little crazy for this kind of people who can train machine learning models and get them into production. Because one thing is to train them in your local laptop and create nice plots there, but another deal is to be able to create them into a service, and to deploy them into a service that can actually serve other services or other clients at a scalable way. So just to give you an example, one way to think about it is that you can become really fast at doing this. And there are a few examples that I've put here for companies that do this in a very fast way. So, for example, Meta does one big deployment a day. So they deploy one big piece of code a day. But for example, Amazon do 136K deployments a day. So if you master these techniques, at least to some degree, you'll be able to be deploying your code really, really fast in a very reliable way and become very, very attractive to employers. One phrase I like to recall sometimes is that there are two types of AI engineers or data engineers or ML engineers. The bad ones are the ones who are able to deploy their code into production. So that's something to think about. Let's see if the run. Yeah, it all worked here at the SEC. Great. You can see the time here. You can see also that it is capped, so the accuracy didn't go as far high as expected, 78%. But previously, when you had the full thing running the full time, the full epochs, it will go up to 98%. So this is capped, so that you can see a shorter run and see results a little faster and check if everything's going right. So great for that. So final remarks. So as I mentioned, there are bad ML AI engineers, and then there are ML AI engineers who actually can deploy their code into production. Another idea to take home is do not commit big resources and time into testing ML or AI models. For that, you can use unit tests. Unit tests are the first thing to do. The first line of testing, you should do that because it saves you time and resources, big time. GitHub Actions are the first step in the automation process, of course, but it's not the only one. There is plenty more that you can learn to leverage your computing practices or your computing capabilities. So there is a ton to learn about that. I'm happy to share some of that knowledge if you want later, if you want to connect with me. And finally, something that a lot of people are saying around is that AI won't take your job or your AI engineering job, but someone who knows how to use DevOps or MLOps to streamline the deployment of AI or ML models into production, those people for sure will be able to take your job away. So be aware of that. I think that's all for today. I wanted to show more, but time won't permit. 11:52, so I think that's pretty much for today. These are my socials if you want to connect with me. Do you have any questions?